At this moment in time, he sets off another one. So that other one starts out there, and then it gets bigger and bigger. At the next moment in time, he lets out another one. So the distance between these waves, that would be the wavelength. Those are both peaks. That's the peak-to-peak distance. So if I'm dealing with a wave that looks like this, it's the distance from here to here, the wavelength. So that is someone standing still, they're shouting, you're sitting there at rest relative to the source, and whatever their frequency is given off, or wavelength that's given off, is the same wavelength that you perceive. All right. Scenario number 2 is that object starts to move. So it begins giving off a sound here, and that wave gets bigger and bigger and bigger. Now it's moving off, let's just say, to the right. So when it gives off the next sound, it is moved this way, so it is here. And then that wave gets bigger and bigger. And then in the last one, the object's here, and it would give off another sound. So notice that these waves are a lot closer together. If this were water and you were a bug on the water, you'd be getting hit by the waves far more frequently than you were in that situation. If you're over here, you're being hit by waves less frequently. There's more of a time lag between it. So as the source gets closer to the observer, the frequency goes up. As the source gets farther away from the observer, the frequency goes down. This is the essence of the Doppler shift. As something gets closer, it sounds at a higher frequency, and as it goes away, it sounds at a lower frequency. If you stand on the side of the highway and you hear that, that's the Doppler shift. You get the higher frequency, and then it suddenly drop down to a lower frequency as it passes you. I guess if it's an electric vehicle, it sounds like it's going to ruin physics forever. All right. Now, if it's sound, this is the high pressure. So it's where the atoms, the molecules in the air are closer together. And halfway between, this is the rarefaction, so this is compression. And rarefaction. Yeah, crossing the T makes all the difference. Now, what if you're traveling faster than the speed of sound? So we start out with the typical. Starts out giving off some sound wave, and that sound wave gets bigger and bigger and bigger. This time, he's traveling faster than that sound wave is traveling. So the next sound is given out over here. So he's traveling faster than the sound is. And so that wave is getting bigger, and then bigger. And then green, I guess green's next. What we have right here, we get these points where I have these two compression waves that are overlapping. What do you think is going to happen?
louder noise?
Say that again?
Like it will be louder.
You're getting quieter as you go.
I thought it would be louder because of the earthquakes.
What's that called if I've got two compression waves that suddenly become louder than they were before?
Constructive interference.
Yes, it's constructive interference. So I get these places where it's louder. Now, I've drawn those very distinct here, but suppose you have something that's vibrating at 400 hertz. That's 400 cycles a second. There's a lot more compression waves that are on top of each other if you're doing a sonic boom. Or if you're traveling faster than the speed of sound, you get much more constructive interference. And what you end up with is a cone. So you get that first wave there, and then you got a second wave there, and then you got another wave there, another wave there, as the object's moving in that direction. And there's this cone here of a whole lot of pressure waves that are built up. It's, you know, you got 2, 3, 4, you got a whole bunch of these waves that are on top of each other. And so it is a lot more pressure coming in, and it's louder. It's more apt to break things. If you watch the Mythbusters, and they had this house out in the desert, and they got somebody to fly a plane at supersonic speeds over it. Mythbusters, worth watching. The faster you go, the narrower that cone is. So if I'm on the ground here, not to scale, and I'm traveling just over the speed of sound, I might have this cone looking like that. I'm first going to hear it when that cone gets to me at that point, and then I will stop feeling it at that point when it's traveled that far. If I have a narrower cone, let's see how well this one works. So traveling even faster, I get hit sooner. Of course, it is traveling faster, but there's much more disruption. So if it's flying over your house, then the things will rattle. Well, one, the engine's louder generally when it's going faster, so that adds to it. And also, you're stuck in the cone a little bit longer. And that's a sonic boom. Now, we can create a sonic boom, in theory, with a whip. With a whip, you basically, oh, my whips are at home at the moment. But the whip, you've got a handle, and then you've got the part, the floppy part, you got the strap that getting smaller and smaller as you go. With the handle, if I have a long handle, then let's think about the torque involved. If I have a long handle, I get the flipping like that, and then with less force, I potentially get greater torque, which gets a wave going. But also with a longer handle, there's more moment of inertia, so it's harder to do that. So there's some optimum length for each person about the size handle that you need. Now, since the whip, exaggerated as it goes, that's sort of exaggerated, it gets thinner as you go. That means I can put a small little wave into the whip. The speed of the wave is equal to the square root of the tension over the linear density. Linear density being mass divided by length. I've got a certain amount of mass right there. As it narrows down, I've got less mass the farther the wave travels. So what happens to the speed of the wave?
It increases.
Yes. So I don't have to break the sound barrier with my hand, which would probably be really bad for me. All I need to do is make sure that by the time that the wave gets to the tip, it's going at least half the speed of sound. The tip is a free end, and what happens is that when the wave gets to the very tip of it, this basically, whatever the speed of the wave is, this goes from down here to up here, and it basically doubles the speed. And so if I'm going, so if I can get the wave to travel near half the speed of sound, it'll double, and then you get that really nice clear top. So let's see if I can find those videos I want to show, which will cover several of these things. Any questions before I show some videos? That one? Yes. Yes, I am. All right, first.
You get that. So by now, if you don't get your moisturized hands on, you'll put it on your
The dog.
All right, could we, Layla, if you could flip the lights, please? All right.
Doppler effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of the road. That's you, and the car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
No flip, no cap, no mess. Just driving sweet.
Oh. All right. So anyway, the longest one doesn't even have to be off the ground, he just needs that, it gets faster as it goes, and then at the very end, it doubles the speed.
What's up? I'm Destin. This is Smarter Every Day. This
All right. That's what I wanted to show you there. Questions? So we'll find out if that gets me banned from some internet sites.
What's faster, the speed of sound or the speed of light?
Speed of light,
Order of magnitude.
more than speed of light, so speed of light. Yes, maybe for now, is about 3 times 10 to the 8th meters per second, and then speed of sound, 343 meters per second. How many of you were told when you were young that if you see the lightning bolt and you count the number of seconds, that's the number of miles away it is? Yeah, I told the same myth to my kids. Anyone else told that, or just
I was told something similar.
similar? Okay. Do you know how many seconds per mile? About 5 seconds. It's not 1 second per mile, it's about 5 seconds a mile. But, you know, I knowingly told my kids a lie about that. I figured it wasn't freaking out. All right, just a quick check, see if there's anything else about waves I wanted to hit. That.
I guess what I was told was less of a line, because I was told 3 seconds per mile.
Okay. So they were a little bit more truthful for you. It's 3 seconds per kilometer.
That's probably why I heard 3 seconds, because the person who told me it probably was thinking kilometers and then said miles.
Ah.
Because they were recently making the adjustment, so
Okay.
probably, or they had made the adjustment at one point and then just changed the unit without changing the number.
Or they just lied to you.
Also a distinct possibility.
But I wonder if people who told it to me, did they know any different, or they heard it, and they were just passing it on? Yeah, they're just, the whole Santa Claus issue also. Do you tell your kids Santa Claus is real or not? I guess that's between you and your kids. Or your parents and you.
Or you could tell them that the Easter Bunny is in charge of Christmas.
Is that what you were fed?
Yeah? No.
Just,
That's an interesting one.
just double lie, so then it remains a lie, but they also miss out on the pop culture of Santa Claus.
Just switch up all the characters of every
Double.
holiday. And the leprechaun is for Easter. And then Santa is for Halloween.
Goblins and ghouls for Valentine's Day?
Yes.
Oh yeah, happy belated Valentine's Day. All right. Let's go talk a little bit about thermodynamics. Not a lot of time. I got 20 minutes.
I have a question about the last part that we were just going over.
Yeah.
Could you go over again about what a standing wave is?
I'm trying to think of how formal that psi was not directed at you. That was, how do I formalize it? A standing wave is, I guess I'd call it a self-interfering wave where it produces nodes and antinodes. Because if it's just interfering with itself, it might just look like a mess, and I've managed that a couple times out there. But the standing wave, that you have these points that do not move and points which move a great deal.
Okay.
Is that sufficient?
Mm-hmm.
Okay. All right, as we last left off with thermodynamics, I come up with the earth-shattering suggestion that the change in energy is equal to the final amount of energy minus the initial amount of energy.